Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on the principle and application of mathematical induction. In the last lesson, we learned about the different types of proofs. Today, we will learn how to apply the principle of mathematical induction for making proofs. Are you ready, students? Let us begin. Let us consider the sum of the first n odd positive integers. If n equals 1, then 1 equals 1 or 1 squared. If n equals 2, then 1 plus 3 equals 4, or 2 squared. If n equals 3, then 1 plus 3 plus 5 equals 9, or 3 squared. Do you notice the pattern that is developing, students? It looks as if the sum of the first odd n positive integers is always given by n squared. We can express this idea symbolically. Since the nth odd integer is always given by the equation 2n minus 1, then the rule that we just discovered may be expressed this way. We have tested this rule with the values 1, 2, and 3. Does this mean that the formula is true for any natural number value of n? Let us test this idea, students. Assign any natural number n to test the rule. But I recommend that you do not select a value for n that is too high, or it will take too long to count all the odd numbers. Go ahead now, students.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. I am certain that you found that this rule is true no matter what natural number you assign to n. I am so sure that I will test it for myself by assigning 11 in place of n. If n equals 11, then the sum is 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17 plus 19 plus 21. This sum equals 121, which is 11 squared. It certainly seems like this rule will hold, but we still have a problem. No matter how many cases we check, we can never actually prove that our rule is true. There are infinitely many cases, so no amount of calculation could check them all. Therefore, we need to prove this rule. We must use the principle of mathematical induction. The principle of mathematical induction is defined by this statement. Given an assertion involving a natural number called n, if the assertion is true for n equal to 1 and it is true for n equal to k plus 1, provided that k is greater than or equal to 1, then the assertion is true for any natural number of n. Let us apply this principle to our problem. It is clear that the rule is true when n equals 1 because 1 is equal to 1 squared. Let us assume that the rule is true for n equals k when k is a natural number. Then 1 plus 3 plus 5 and so on plus 2k minus 1 equals k squared. Now we need to show that the rule is true for n equals k plus 1. That is to say, 1 plus 3 plus 5 and so on plus 2k minus 1 plus 2 times k plus 1 minus 1 equals k plus 1 squared. We can simplify this to 1 plus 3 plus 5 and so on plus 2k minus 1 plus 2k plus 2 minus 1. Simplified even further, the equation is 1 plus 3 plus 5 and so on plus 2k minus 1 plus 2k plus 1. We make the assumption that 1 plus 3 plus 5 and so on plus 2k minus 1 equals k squared. Then 1 plus 3 plus 5 and so on plus 2k minus 1 plus 2k plus 1 equals k squared plus 2k plus 1. K squared plus 2k plus 1 can be factorized into k plus 1 times k plus 1 or k squared. Therefore, the rule is also true for n equals k plus 1. By the principle of mathematical induction, we have proved that the rule is true for any natural number n. Please select a partner, students. It is time for another activity. Here is another statement. Can you apply what you have learned about mathematical induction to prove this statement? Please go ahead and try to do this now.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. Did you manage to prove this statement? Let us check your results together. When n equals 1, the statement is true, as demonstrated here. Let us suppose that is true for k, for n equals k. This assumption would be expressed this way: 1 plus 2 plus 3, and so on, plus k equals k times the sum of k plus 1 divided by 2. Now, by adding k plus 1 on both sides, we get this result. We find that k times k plus 1 divided by 2 plus k plus 1 is equal to the product of k plus 1 multiplied by k over 2 plus 1. This is equal to the product of k plus 1 and k plus 2 divided by 2. This is equal to the product of k plus 1 and k plus 2 divided by 2. This in turn is equal to the product of k plus 1 and k plus 1 plus 1 divided by 2. You see, students, that by using the principle of mathematical induction, we have come full circle. The statement is true for k plus 1. Therefore, the statement is true for every natural number of n. I hope you managed to make the proof, everyone. We have reached the end of this lesson. We have learned about the principle of mathematical induction, and we will continue to study it in the next lesson. Until next time, thank you, teacher. Thank you, students.